Oh, hi class. Welcome to the end of surface water hydrology in the time of COVID. And you're going to use a lot of the concepts and techniques that you've used in the last few weeks to complete a Rosgen stream classification of your nearby stream. So you've done a lot of these elements. Whether you did it on the same stream or not, it could make your life easier or more difficult. I kind of hope that you haven't, so you get to learn a new stream and employ these techniques anew. So what you're going to do is you're going to classify based on this. Your textbook has a similar form, but this one's I think easier to actually accomplish, even though it looks slightly more complex. And the first thing you're going to do is we need to establish entrenchment ratio. And you know how to do that already, because what you need is bankful width and you need the width of the flood prone area. And if we had surveying equipment, we could go out and do it properly, but I've also included these screenshots and how to get the flood prone area and the rough estimate of what it is via Google Earth. And you are going to get an elevation profile and then make your measurement from where you think the flood prone area is based on stream morphology and the cross-sectional profile. And then you're going to get your bankful width. And if your stream is as large as mine, it's pretty hard to get all the way across. So I just use Google Earth to give me a measurement. And you can see it right there. All these slides are also online for you. So from bankful width, flood prone area, I can easily calculate my entrenchment ratio. And I've done so right there, and it's 3.15. Okay, so let's go back to our sheet. And 3.15. Okay, single thread channels, yes. Entrenchment ratio, less than 1.4, nope. 1.4 to 2.2, nope. And a ratio greater than 2.2, that's us, yeah. We had an entrenchment ratio on my stream of 3.15. Okay, next thing we do is width to depth ratio. And this, you can take your Google Earth stream bankful width measurement, and then you will have to go to a stream to get this estimate. So you need to get the depth, basically, and this is what you did, I think, on our first lesson of the COVID crisis. So I'm not going to send Mira out, although I wish she would go, but my stream here is over 2 feet. How do I know that? Because I'm wearing these cool boots, and my boots from heel to toe is about a foot, and it's about knee deep out there, so I know it's about 2.2 feet. Okay, so I take my depth and I have my bankful width, and then I can generate, bear with me for a second, I can generate my width to depth ratio. So my width of stream is 68.27 feet. That's about right for here. That's about 6 basketball goals tall, and it's about 2.2 feet. And that's a width to depth ratio of around 30.7. Okay, so I already selected this. My entrenchment ratio is greater than 2.2, and I need my width to depth ratio. Okay, it's greater than 12. Is that true for me? Yeah, it definitely is. It's 30. Okay. So we are definitely here. Moderate to high width to depth. Okay, and then we need sinuosity. And I've tried to explain this before, but if you are looking at this system, you can see it's bending around the corner. We're following it down. I know that this system is rather sinuous. Oh boy. Oh. And I've included how you can get this measurement on Google Earth. So you can get a straight line measurement from here to here, and I just put pins on the Google Earth page up there, all the way down to the bend in the stream here. And that gives me a measurement of, let's see, ground length 2,704 feet. Okay, and then I'd made a path in the stream, like where if Mira was traveling down that same length to get from point A to point B, but doing it in the stream, Mira's going to cover more distance, right? She's kind of zigzagging along the same path, and when you straighten it out, it's going to be a longer path to travel. And so then I mapped the stream zigzag path, and that length was much higher. It's 3,200 feet versus an sort of the way the bird would fly, 2,700 feet. And then you divide that, you divide your channel length by your straight line length, and I got a sinuosity of 1.18. So I've got a slightly entrenched stream, I've got moderate to high width to depth ratio, and then I have something that's greater than 1.2. In fact, I have, what did I say, 1.1, basically 1.2. It's 1.18. So I'm in stream type C. Okay, that was pretty easy. And now I can get even finer. I can decide which category on type C this stream really is. So then we just need the slope. And my slope for this stream, basically I used the same measurement here, and I took my elevation at one end of the stream, basically up there beyond Mira in the grass, and I took the elevation above sea level, and then I took the elevation point at the end of my reach down there, and then I subtracted it, and I came up with a drop of 38 feet from up where way beyond Mira down to the bottom of where I'm analyzing my reach, and you drop about 38 feet. Okay, and from there I generated a slope, and this part's a little tricky. Usually, like on road signs in Western Maryland, you'll see slope expressed as a percentage, and basically you divide the two numbers, your 38 divided by whatever your run is. In my case, it's 2,700 feet, and then you multiply that value by 100, and that would give me 1.40. I'm not confusing you, because that's the way we typically do slope, but in this case they just want the slope fraction, so you just divide 38 feet or whatever your drop is from point A to point B by the distance, and then you don't multiply it by anything, and you'll get a fraction. And in my case I got 0.014, and it is going to be 0.014, and it's in between these two values. So then that brings us to the next section, where this is the last part. You need to look at the channel materials. Is the average from your Woolman pebble count telling you that the bottom is mostly silt and clay, or sand, or gravel, or cobble, or boulder, or bedrock? And in my case, it is going to be cobble, because I could go and do another Woolman pebble count, or I could look up here on this point bar, and I can tell that most of mine are cobble. And then that's going to tell me I was over here, and I am at a C3 stream. Done. That's what kind of stream this is, and that's all I'm really asking you to do. And then you're going to look up and tell me a little bit about what a C3 stream, or whatever your stream might be categorized as, and what that means. What are its risks? Is it vulnerable to certain threats? And this is the way, kind of like the Munsell color chart for soils, that we standardize our stream measurements. And Rosgen's classification, although it seems a little confusing at the beginning, is the going method. It is basically the Munsell color chart of surface water hydrology, or stream morphology. I think this might be our last video. Maybe we have one more, I don't know. We'll see what how you guys do on this project. But if it is, I want to thank you all for being in this class. I'm really, really sorry that it turned out the way it did, and we didn't actually get out on the streams together. We also had some restoration projects to do with Trout Unlimited, but another time. But Mira and I appreciate you guys giving us something to do. while we're off in quarantine, and a chance to get to know the Credit River a lot better than I did before. Okay guys, over and out. I'll talk to you soon, I hope. Bye.